Hello, everybody. Mr. Hasty here again. Today we're going to be talking about applications of calculus in statistics, and we're particularly going to be talking about probability distributions. So let's talk about what probability distributions are. So we're going to talk about this in terms of two concepts you already kind of understand. We're going to give them formal names. The first one is a uniform distribution. Now, we all understand a uniform distribution. You might not know that term, but if you've ever played a game with cards or a game with dice, you know it. So let's say we're rolling a dice. A uniform distribution means that you have equal chances of getting any value that is in the possible set of outcomes. So if you roll a dice, there's equal chances for each one. So the probability is distributed equally. Each value gets an equal share of the probability. These are very common in what we call discrete cases. Cases where when you roll a die, you can get a 1, a 2, a 3, but you can't get a 2.5. So we use these oftentimes for discrete cases. Now, we're not going to use those that much. That's just one type of probability distribution you're used to, where all of the things that you could possibly get have equal probability. So let's talk about something that is not uniformly distributed. It's going to be what we call a normal or a Gaussian distribution, named after Gauss, the famous mathematician. Okay, a normal or Gaussian distribution tends to be centered together. So let's go back to the dice. If you roll two dice and you add them up, I'm going to make a little table here. Some things are more likely to occur than others. Oh, am I going to run out of room? Got to squeeze it. Boom, perfect. So I'm just adding up the possibilities that we would get. If you roll the two dice and add them together, what would you get? We get 3 here, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 11, oh, nope, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So in this case, 7 is by far the most likely outcome. This is a situation where we know that the things in the middle, the average, because if you think about two dice, you have a possibility of 1 to 6 and a possibility of 1 to 6. So if you think about it, it's an average of 3.5 per dice, which means that you have an average total of 7. The average is much more likely to occur than, let's say, an extreme case like getting a 2. These follow what we call a normal distribution. And a lot of things we talk about with the average, like the average IQ, the average height of a person, the average weight of a fish, follow this property where more things fall into the middle, fall towards the average value. And as you get further from the average, they get less and less likely to occur. In a uniform, when the average is right here, it doesn't make 3 and 4 more likely to occur than 6 and 1. It just means that that's where the average is, but it doesn't affect the distribution. In a normal distribution, we have to know the average. We actually have to know another piece of information that's called the standard deviation. So standard deviation is a new concept for us that we're going to get into here in a second. So let's dive a little bit more into this normal distribution. So these will create what we call bell curves. Bell curves look like this curve I have here on the screen. They have a property that they tend to be big in the middle and then get lower on the sides. They never get to 0. They have that property as well. They have an asymptote at 0. And they have this property that the area of the region, for instance, we look at the pink region, would give us a probability of falling within a particular range. Now, to use these, you need to have two pieces of information. You need to have the mean, or the average, which in statistics is given the Greek letter mu. And you need to have the standard deviation, which is given the Greek letter sigma, lowercase sigma. So the concept of standard deviation is that it measures how quickly and how much something spreads out from the average. So things with high standard deviation tend to vary greatly from the average. Things with low standard deviation tend to be pretty close. So for instance, if you're manufacturing something that's supposed to weigh, let's say, 10 ounces, you're going to try to make sure they're pretty close to 10 ounces. There might be a little give or take here or there, so you want a low standard deviation. But if you're measuring something like the average length of snakes in the world, well, there are some really long snakes, there are some really short snakes, and so that would have a greater standard deviation. Now, the formula is pretty intense, and I'm not expecting you to memorize this formula. The formula for a probability density, f of x, is equal to 1 over sigma root 2 pi times e to the exponent negative parenthesis x minus mu squared divided by, still in the exponent, the quantity 2 sigma squared, end quantity. And like I said, it's pretty intense. Important things to note: the squared goes outside of the parentheses on top and inside of the parentheses on bottom. Now, what does that particular function give us? This spits out, if we put in a value, like let's say we want to know how likely a certain value is to occur in our data set. If we plug in a value, the function is going to spit out a probability density function. Which are abbreviated PDFs. Before that was a different thing. Now, the important part you need to know about probability density functions is not so much we're not going to use those directly. We're going to use the integrals of those, because the integrals of those are the areas under the curve, and it turns out the areas under the curve are the probabilities of being in a certain range. So before we get actually using calculus here, let's talk about something called the 68, 95, 99.7 rule. And this is something commonly learned in statistics classes before they have a general understanding of calculus. So if we look at, I'm going to clear this real quick. If we look at this right here, the center of the graph is always at the mean, is always at the average. And then you'll notice that on each side it says mu plus sigma and mu minus sigma. And so what this is essentially breaking the graphs up into how far off of average you are. So everything in the pink region is from 1 standard deviation lower to 1 standard deviation higher. And it turns out that every normal curve, 68.27%, or roughly 68%, of values will fall between 1 standard deviation lower and 1 standard deviation higher. 95% will fall within 2 standard deviations. So that'd be from this edge here to this edge here will be 2 standard deviations. And 3 standard deviations from here to here would be 99.7%. So we're going to go into some examples of this, and we're going to start off by using the 68, 95, 99.7 rule. So I got this information from a public source stats site. The average height of an American woman over the age of 20 is 65 inches tall. So that'd be 5 foot 5 inches tall, with a standard deviation of 4 inches. So what that means is that the average right in the middle, if we look down at our graph here, is 65 inches. If we go up 4 inches to 5 foot 9, right, and we go down to 5 foot 1, which is 4 inches south, 68.27% of the population of women will fall within that category. And remember, it's important, I should say specifically American women over the age of 20, but I'm not going to repeat that phrase every single time. So if we looked at it and we did 2 standard deviations, so that'd be 2 standard deviations would be 8 inches. So 8 inches shorter than 5'5" is 4'9", and 8 inches taller than 5'5" is 6'1". So if we look at it, between the heights of 4'9" and 6'1", 95% of the American female population will fall into that height range. So now let's talk about these problems and construct our calculus method. Part A, what is the probability a randomly selected woman is between 5'1" and 5'9"? We talked about this a little bit. 5'1" is exactly 4 inches shorter than the average, 1 standard deviation, it's right here. And 5'9" is exactly 1 standard deviation above. So we can actually shortcut this. We don't need to do the calculus. We know that between those two variants, we're going to have 68.27% of the population fall within that category. Now, part B. This is where we're not going to be able to rely on this little trick anymore. It says, what is probably a randomly selected woman between 5 feet? That would be right here. And 5'11", which is right there. So we know it's more than 68%, but we can't work with it because it's not on those exact markers. And this is where the calculus is needed. So we have to construct that formula that we talked about previously. So remember, in this situation, mu is 65 and sigma is 4. So f of x equals 1 over 4 root 2 pi. And I'm literally just putting the numbers into that really massive formula that we had a second ago, times e to the negative quantity x minus 65 quantity squared divided by, running out of space here, 2 times 4 squared, parentheses. Now we could clean some of this up, like the 2 times 4 squared and all that good stuff, which you can do when you put it in your calculator. Because we're going to use a calculator for this, we're not going to do any of this by hand. So how do we apply this? Well, the integral will give us the area under that curve, and the area under the curve is the probability of landing within that region. So we're going to have the integral of that, which I am not going to rewrite every time. I'm just going to call it f of x, because we're going to use that same function for each example. But what are the bounds? We got to make sure that we convert everything to inches. So 5 feet tall would be 60 inches on the low bound, and 5'11" is 71 inches on the high bound. We plug that into our calculator, and we get 82.754%. Now, that stands to reason because we know that the pink region, which is smaller than our region, is 68, but the blue region, if we extend all the way out to the blue region, is 95. So we should be somewhere in between there. So a couple notes about putting this in your calculator. You need to be very, very careful you put it in correctly, obviously, because it's a complicated formula. The second thing is bounds. So your x's represent the values of whatever you're talking about. So the height. So in this case, I went from a low of 0, which is way lower than we need, to a high of 84, because 84 inches is divided by 12, about 7 feet tall. So that's a pretty extreme case for height. And for my y values, remember, the highest probability you can ever get is 1. All probabilities are between 0 and 1. We list them as percentages, but really the number we get here is 0.82754, not 82.754. And so I always list my probabilities. Pretty much my y values are always from 0 to 1. Now, sometimes that will be so low that you can't even see your curve. If you did like 0 to 0.5 or 0 to 0.2 or 0 to 0.1 even, it's easier to see your curve. But I was able to see the curve with these bounds. All right, part C. What is probably a randomly selected woman is over 6 feet tall? So we're still going to use the same function. And 6 feet tall is 72, and that's the lowest we'd want, 72. But what's the highest? We can't really put infinity in there and it actually breaks what we want. What we have to do is look for a realistic number for a high end. So you could do some research. You could research what's the tallest woman in the world and then kind of set your bar there. But basically there's kind of an easy rule. If you're at 99.7% of the population after 3 standard deviations, if you do 6 standard deviations, 6 sigmas, that is way higher or way lower than what you really need to be considering. So what we're talking about here with 6 sigma is that's 6 times sigma, so that's 24 inches higher than the average. Remember, the average was 65 inches. So if we go 24 inches higher than that, that'd be 89. So we're going to go from 72 to 89. And that's just a little trick we use when we have something that's unbounded. Let's say we want to know how many women are shorter than 5'1". We'd have to go 5'1", and we could go down to 0, but it's easier just to go to 6 sigma. If we're going higher, though, we really need an upper bound. And so 6 sigma, whatever that happens to be in that case, is what we're going to use. So we do the calculation on our calculator again, and we get, and as I was doing that, I kind of remember that we only had a window up to 85, so I had to up my window to 90 to cover that. And I got 4.006%. So there are very few women over 6 feet tall. And you probably know some. And you're like, well, that seems really low. But we're talking about 4%, so that's 4 out of every 100. So there's a couple hundred people at our school. That means there's going to be a few women who are above 6 feet tall. Finally, part D. And part D is a bit tricky. I'm going to clear some of this. So, what is the probability that a randomly selected woman is exactly 5'5" tall? So there's really 2 contexts to this problem. One is a strictly mathematical approach in which the answer is going to be 0, which doesn't make much sense to us. Or there's a kind of more intuitive approach here. So the first thing is, if we're talking exactly 5'5" tall, that's the average height, and that's 65 inches. So we're going to go from 65 to 65 f of x dx. And we shouldn't even need to put it into our calculator to know that's going to come out to be exactly 0. And that seems silly at first, but if we think about it in strictly mathematical sense, what's the probability that someone is exactly 65 inches tall? We're not talking about 65 kind of close. We're talking about 65.000000000000000 forever. And the chances are not good. They're very, very low that somebody's not going to be like a fraction of a fraction of a fraction of a fraction of an inch taller. So what we need to establish here is kind of like, well, what's our like would we call someone who's 65.112 inches tall? We would need to establish some kind of like things where we're going to say, oh, well, they're just 65. And so what we're going to do there is we have to kind of make a case here. And there's no perfect answer here. So if we're going to do the integral, what I'm going to do it from is I'm going to have a low bound. I would say anybody above like 64.5, right? Like about half 64.5 to about anybody 65.5. Of f of x dx. And I think that's a pretty good estimate to answer that question as it's intended. But you got to use some discretion there. And I got 9.948%. And that seems reasonable to me. You might be like, well, if it's the average, shouldn't there be more? Well, just because it's the average doesn't mean there has to be a ton in that particular space. That's why the standard deviation matters. The average on 6 dice is 3.5, but that's not even a possibility to occur in that situation because it's discrete. This is continuous, however, so we should find some people in that range, and we do. We find about 10%. That's 1 out of every 10 American women over the age of 20 that has that particular height range. All right. So that covers our discussion of statistics and kind of wraps up chapter 7.5. See you guys later.